Hey guys, welcome back to Introduction to Computer Networks. And this is week 15, episode 27. We're just 1 week away from the final exam, which means the summer is just around the corner. All right. As usual, let's check out what the assignments are this week. So, hey, we are done with the PAs. Okay, great. And all that remains are just 5 more quizzes. Okay. I think chances high that we'll be doing all 5 of them tomorrow, but we'll see. We'll see. Okay. We might have time to do quiz 49 today. So what I want to say is that quiz 49 is straightforward. Okay. 50 to 53 are straightforward at the beginning and then growingly complex. Okay, but there are quizzes in a series. Okay, you've done a quiz series before, so you know how it's like, right? Polly likes to start from cases that are straightforward, so you get some sense, and then gradually increase the complexity, then you get more sense. Okay, and eventually you get the full picture. So once again, these are due on Saturday. And next week is the final week. So a lot of times I will cancel the lecture next week depending on how the class progress over the semester. And I think it's okay. Let's cancel the lecture next week. We should be able to cover all the content till within the scope of the exam 3. So if you go to exam 3 channel, you will see the exact scope. So yeah, I think that's at the top. Okay, by the way, the final exam is next Wednesday. And it will be at the same time window as all the Wednesday lectures. And the procedure is the same, right? So we will do ID check, right? And then we'll announce the beginning of the exam, and you will see all the usual things that we did already in exam 2 and 1. And we will count to 90 minutes until the end of the exam. So similarly, for exam 3, if you need to go early, just let Polly know. Okay. Sometimes Polly will be a little bit slow discovering that you did try to talk, but it's okay. Hopefully, okay, be patient with Polly, because usually during the exam, I can be a little bit occupied, okay, with things. All right, so the scope is PA 8 to 9, and it will cover chapter 4 and chapter 5.1 to 5.4. All right. So in fact, the end of last week's lecture, we have already started 5.4. That is the first video overviewing how the two routing algorithms, link state and distance vector, are used for the internet. And if you paid attention, or if you are still in the lecture at the end of last week, is that we use a combination of these, because we actually divide the routers on the internet, and so that they will run in 2 levels. Okay, at the lower level, within a network, within a autonomous system, right? The administrator of the autonomous system can decide which routing protocol he or she wants to use, which is a lot more flexible, and the system admin can decide depending on whether reliability is important or memory cost is important. Lower memory cost is important, which protocol to use, isn't it? As you see also from our polls earlier, you guys have different ideas of which protocol you want to run. And if you get to be the system admin of your domain, of your autonomous system, of course you get to choose, right? And so within an autonomous system, within an autonomous domain, the system admin gets to choose which one to run. But to connect all the domains on the internet, across all the domains, across all the ASs, autonomous systems, are called the AS for short for the rest of the lecture this week. Across the autonomous system, we need to have one unified routing protocols, right? Otherwise, one autonomous system might not reach another autonomous system, okay? So that particular protocol, okay, is very similar to distance vector, but not exactly distance vector, okay? But you get a rough idea from last week at the end that the internet routing runs in two levels. There's the inter-AS level and then the intra-AS level. Okay, so the first video today, okay, is to talk more about these autonomous systems, and we'll talk about intra-AS routing, okay, and we'll also introduce inter-AS routing. And you will see also how intra-AS routing and inter-AS routing interplay. All right, so these are what the first two videos are about. So the first video is to give you the detail of intra-AS routing. So all the routers within an autonomous system is an intra-AS router. Okay, but there are some routers in the within the AS are special. They are called the gateway routers. And the inter-AS routings run on these gateway routers, okay, so that the gateway routers of a domain can exchange with gateway routers of another domain, and therefore knowing more about a particular destination, which way to send the data for a particular autonomous system, a destination autonomous system. Okay, so this video, 4 minutes and 22 seconds. Essentially, you hear Polly introducing intra-AS domain, and then inter-AS domain, and a very brief example of inter-AS domain routing. Once again, on the internet, we aggregate the routers in a region and call it the autonomous system, an AS. Or sometimes we also call it a domain. So the internet is a network of ASs, a network of domains. The routing protocol within the AS, the network admin configuring all the routers running, is called the intra-AS routing. So you see here, it's the routing protocol running among all the hosts and routers in the same AS. All routers in the same AS will need to run the same intra-AS protocol. Now, routers belonging to different ASs can then run different intra-AS protocol. That is an independent, autonomous choice of the network admins individually. Now, each AS will also pick powerful routers, usually sitting at the border of the AS. These powerful routers, I call them the delegate routers earlier. Yeah, here you see a more formal way of calling them are the gateway routers. Gateway is what? The doorway. Yeah, the routers sitting at the border of these AS connecting to another AS. Okay, so gateway routers, powerful delegate routers, will be sitting at the edge, the border, of its own AS, and have links both within towards routers within the AS and links to routers in other AS. And therefore, this routing protocol, running in the backbone of the internet, is called the inter-AS routing. Okay, so that is the routing protocol that's running across the gateway routers. So this is the routing, working among the ASs, and the gateway router there will be doing the inter-AS routing computation. And on the slide here, you see an example of ASs and how ASs interconnect. So we do have 3 ASs, 1 here, 2 here, and 3 here. You see individual routers interconnected within one AS. Okay, so there are 3 here for AS2 and 3 more here for AS3. Now, AS1, 2, 3 each could run its own intra-AS routing, but you see 1B and 1C, both of these routers have links internally as well as externally. So 1B and 1C are the gateway routers. So these 2 gateway routers. Just like 2A for AS2 is one of the gateway routers. 3A for AS3 is one of the gateway routers. And inter-AS routing is running in between. 1B, 2A, 1C, 3A, and so on and so forth. Now, the focus of this slide is to talk about how would the forwarding table look like when we have 2 levels of routing running on the internet. Now, let me show you an example here. 1D is one of the routers existing on the internet. What's going to happen there is the forwarding table is not going to be just contributed from the intra-AS routing algorithm. It would also be contributed from the inter-AS routing algorithm. As you see earlier, in order to pass data from one router to another router that's far away, okay, not within the region, right? You need intra-AS routing to find the gateway router. And you also need the gateway router, okay, to find, hey, where's the destination gateway router? All right, so you do need inter-AS routing algorithm telling, okay, each node where to pass data further. Just like you need intra-AS routing there telling you, okay, how to reach another router within the AS. Okay, so forwarding table here will be configured by both intra and inter-AS routing algorithm. The intra-AS routing determines the entries, okay, for destinations within the AS, okay, within AS. And inter-AS, okay, determines entry for the external destinations. Okay. To be precise, the inter-AS determines which gateway, okay, which router here you should be passing the data to. Okay. But intra-AS will also be telling 1D here, okay, to go to that particular gateway router, what is the right way? So you see here, interplay of inter-AS and intra-AS routing for packets going outside of the AS. All right, so that's a brief example. But what's very important in the video is that, yeah, of course, the routers within a domain would run intra-AS routing, right? And some of the routers would run the inter-AS routing, okay? But after all these routing protocols are done computing routes, hey, there's a forwarding table, right? Each of the router would need to establish, right? Recall, this is network layer, right? We have two planes. One is the control plane doing the routing. The other is the, data plane that is doing the forwarding. So that forwarding table is a little special. Every router will have this forwarding table, okay? And every router's forwarding table will contain entries to support sending to destination within the domain, but also entries supporting sending to the destinations outside of the domain. All right, even though a intra-AS router, so a router which is not a gateway, there will still be entries in the forwarding table that has destination outside of the domain. All right. So internet routing is interesting in a way that the operation is a little bit more complex. Okay, the operation is a little bit more complex and a lot of times more manual, not strictly based on a computation logic. Okay, good. Now, next, okay, let's focus a little bit more on the inter-AS routing. All right, inter-AS routing, you heard Polly saying it already, right? So it's very much like distance vector. If you recall distance vector routing, it's an endless loop of 3 steps. Recall? Each domain begin by announcing, right, its initial distance vector. Yeah, and we know how to do the initial table, isn't it? How we do the initialization, going through a series of quizzes. But that distance vector, right, after initialization, will need to what? Be propagated. All right. So that initial distance vector table for distance vector routing is necessary. And in fact, it's the very first step, okay, of what distance vector routing do. But in inter-AS routing, okay, we said that it's not exactly distance vector, right? Later on, you will hear exactly what routing protocol it is. So, but it's very much like distance vector, right? So there needs to be something that's initialized, right, by each of these inter-AS routers or each of these gateway routers. And then you send that initial tables, okay, and propagate it throughout the entire internet, okay. Interestingly, the authors of the textbook often refer to this initial table, okay, at the higher level of internet routing as reachability information, okay, reachability information. So it is saying that at the higher level, inter-AS routing, each AS will need to announce its reachability, its existence, to send its initial table to begin the path vector routing with. All right, so this next video explains that, okay, how the inter-AES routing works and how it interacts, again, with the intra-AES routing. To make sure the interplay of the intra-AES and inter-AES routing is more clear, okay, let's take a step back. Okay. Look at AES1 here, 1A, 1B, 1C, and 1D. Okay, so these routers within AES would run the intra-AES routing. Therefore, they would know the shortest path going to each other. No problem. Now, at a higher level, at the inter-AES routing level, so we have these gateway routers. 1C and 1B are the gateway routers of AES1. 3A, obviously a gateway router for AES3. But you see here, 3B having also connectivity to outside to another AES. 3B is also a gateway router for AES3. Similarly, 2A, 2B, 2C all have links to outside to other AESs. So they are also gateway routers. So these gateway routers at the higher level will be running the inter-AES routing, so that's another routing protocol, and they will all be running the same routing protocol. They will exchange information to each other using the link state or the distance vector routing to come up with the shortest path. But this time, the shortest path is what? Oh, if I want to go from AES1 to AES2, the shortest path is to go directly from AES1 to AES2. Now, if there is another AES here, AES4, for example, okay, then the shortest path might be to go from AES1, AES2, and then AES4. So these gateway routers will maintain shortest path, but shortest path in terms of, what is the next AES to the destination AES? What is the next AES to the destination network? Okay. So we might have another AES here, AES5. Then the shortest path from AES1 will be what? AES1, AES3, and then AES5. With those said, we may now walk through the scenario here. Let's suppose a router in AES1, say 1D, and it's got packets to go outside of the AES. Let's say AES5 here. Okay. Now, we see the shortest AES path will be the what? A1, AES3, and then AES5. And this information will be available here at the gateway router, 1C, 1B, 3A, 3B. But 1D here as an internal router. So this router here, we'll have actually trouble judging, right? Among the two gateway routers, 1C and 1B, which one of these 1D should be passing the packets to, so that these gateway routers will be able to pass further to the neighboring router along the shortest path to the destination. This is also saying, even though these routers are internal, they participate in intra-AES routing. They do not participate in inter-AES routing, but they need still to know the shortest AES path to these destination AESs out in the world. Okay. So 1D, 1A don't do inter-AES routing, but they still need to know the inter-AES path. Okay. So they must learn the inter-AES path, which is to know for each destination AES, is it AES2 or AES3 being the next hop AES to the destination AES? And this is essentially the inter-AES routes. And how? Okay, how does 1D and 1A learn? Well, you know what? 1C and 1B do participate in inter-AES routing. So 1C and 1B thereafter, inter-AES routing will then propagate these AES path information to all routers inside AES1. And so propagation of the AES path, just like computation of the inter-AES path, would also be part of the job of the inter-AES routing. All right, so that video very important, right? As Polly said, the intra-AES routers don't do inter-AES routing, but they still need to know these AES paths, to the domains out on the internet. All right. Later on, when we start talking about exactly which protocol we use for inter-AES routing and how the inter-AES routing on the internet interact with the intra-AES routing, you'll see exactly how that forwarding table is established. Okay, at this moment I understand it sounds a little bit fuzzy, but later you will see examples, okay, that is concrete. All right, now we move on to talk more about each of the categories. First, we'll talk about the intra-AS routing, okay. Hey, within an AS, one can choose whichever, okay, routing protocol you prefer. Therefore, yeah, you see that there are actually several options one can choose to run the intra-AS routing on, okay. In this video coming up, we will introduce 3 of these, okay, from the older ones to the newer ones, okay, from the public ones also to some proprietary one. All right, so this video, 3.5 minutes, okay, 3 varieties, and later on we'll focus on one of the varieties and talk a little bit more.
The first big category is the intra-AS routing. Okay, so this is the routing protocol runs on the routers within an AS. It's also known as the interior gateway protocols, IGP. And here, interior gateway, not to be mistaken with the gateway routers. So gateway routers are the routers sitting at the border of an AS, having connectivity to other ASs. So gateway router there are to interconnect ASs. But interior gateways are completely internal. Okay? And then running on these internal routers within an AS, we have 3 very well-known protocols. RIP here, not really standing for resting in peace, it's actually Routing Information Protocol. Okay? But if it adds the impression, RIP, this protocol is also the oldest, okay, implementation of an intra-AS routing. It came with the Berkeley's BSD distribution, okay, in the 1980s, late 80s. And it's based on this principle, distance vector routing. Okay. Yeah, nowadays I'm not quite sure. I don't know if any network admins is running RIP for their intra-AS. Okay. But this other one, OSPF, short for Open, Shortest Path First Routing Protocol. This one, on the other hand, is very popular. Okay. So Open here stands for open source. Okay. RIP is also open source as it came with the BSD. So it runs also the shortest path first routing. Yeah, you guessed. Yeah, it's the Dijkstra shortest path algorithm that's running, and therefore it's based on the link state routing principle. And to make sure that we credit the right people, OSPF is actually based on ISIS. It's another routing protocol that was designed maybe 3 decades ago, okay, by early researchers for distributed system research as well as these multiprocessor system research. So in those paradigms, having multiprocessors, if you want to pass the messages around, and these processors are actually forming an interconnected network, you also need to find a path to go from one processor to another processor. Okay, so at the time, okay, those researchers, those computer scientists, have designed ISIS for the purpose. Okay, OSPF for internet, which is also a distributed system. It's just that it's very loosely connected distributed system. Yeah, borrow much of the design principles from ISIS. Third one is called the IDRIP, IGRP, Interior Gateway Routing Protocol. Now, this one is completely closed. It's Cisco proprietary. Okay. It came with these Cisco routers, but it only is maintained until 2016, okay, and obsolete afterwards. The reason for that is because Cisco is also beginning to embrace the idea of doing software-defined networking. Okay, so if you recall, in software-defined networking, routing is all done in the remote controller on the powerful machines. So the routers there, okay, in SDN, pretty much are doing what? Generalized forwarding, okay, and allowing the flow table being installed, and that's pretty much all. Okay, there's no need of running routing algorithms on individual routers. Okay, so starting from 2016, Cisco stopped maintaining IDRIP because there's really no need, very little need of doing routings inside the router.
All right, so 3 categories, okay? And those who follow the lecture closely see Polly had a pop-up quiz, okay? It is about, among the 3 varieties Polly introduced in the video, which, whether RIP is based on distance vector or link state, guys? All right, so I see Yu Zheng and Bo Yuan follow the lecture closely. Good for you guys. And next video is to discuss more about OSPF. Okay, OSPF is super popular these days. Okay, and for a very good reason. Okay, it's not strictly because it's link state, which is easier to manage, easier to debug. Okay, it's also because of two additions. One is called security. Yeah, so can you imagine these reachability informations or the link state reports being sent but somehow hijacked by hackers? Oh, wow. You know what? It has happened before that hackers actually injected routes announcements such that it creates a black hole, okay, on the internet. So it sucks in a lot of data and information. And these data and information never get to the destination. Okay, so it was a big problem. Okay, so you see that OSPF here with encryption, okay, secure sessions connecting the routers at the intra-AS level is very important. So security is one very important extension in OSPF that makes it popular. Another is that OSPF, unlike the plain link state routing, is extended to run in a hierarchical way. So you see, distance vector can run in a hierarchical way. Distance vector is by nature hierarchical. But link state, right? Well, a router needs to know the entire topology of the network. That is what limits link state. But perhaps, right, one can design a hierarchical link state, right? So the lower level knows every node within the subnet, okay, of the entire autonomous systems. And each subnet, if you consider it as a node, right? So one can create a topology of the higher level nets, the network of subnets, and do link state routing there. How about that? So OSPF with important extensions, two of them very important, security and hierarchy. Okay, so this video is then you can hear from how Polly has introduced it. Very long, 6.5 minutes.
Yeah, let's speak a bit more about the most popular routing protocol here in the intra-AS category, the OSPF. Open here stands for, yeah, the protocol is open source. Second, the SPF stands for the routing protocol is based on the link state principle. So we do distribute the link state reports all over the network. Therefore, each router will be able to reconstruct the global network topology. From there, then we call the Dijkstra algorithm to compute the shortest path. Be a bit careful though, these routers sending these link state reports, okay, they'll be sending these reports in OSPF message. These OSPF messages are native IP packets, meaning the message itself, and then we append the IP packet header, and that's all. Okay, there's no TCP, UDP, or application layer header on top of that. Yeah, inside these link state advertisements, it's going to contain, hey, who the neighbors are for this router. Also, the cost of the link leading to connecting to these neighboring routers. Again, ISIS routing, this is the predecessor of OSPF designed by the early distributed system researchers. Now, what we haven't mentioned much yet are these. So these are the advanced features of OSPF. First of all, okay, these OSPF messages, very important link state reports, okay, they can be sent through a secure channel such that the receiver of these link state reports can authenticate, okay, the sources of the sender, therefore preventing malicious attacks. Okay, so yeah, if people can just send these link state reports around, okay, with no security check, one can easily inject a false route, okay, into the system. Second feature is this. One can actually exploit multiple same cost paths. Okay, so in case we come up with the topology such that the Dijkstra give us same cost paths and there are multiple of them, we could actually send data over these multiple same cost paths, okay, which is nice, okay, sometimes. For each link, the metric for the link cost, okay, can be defined also differently for different type of services. Okay, for example, if we are trying to serve best effort traffic, meaning traffic does not require timely delivery, okay, so the receiver can wait longer, then the cost of a satellite link, which the delay is longer, can be set lower, right? Because you would then prefer using the satellite link if the data does not require timely delivery. On the other hand, okay, if the data is real time, okay, then set the satellite link costs high. Therefore, we avoid choosing satellite link along the path to deliver the real-time data. Okay. And oh yeah, it allows also, OSPF allows also integration of the unicast and multicast. Now, if you recall in Dijkstra algorithm, in the end of the algorithm, what we ended up generating is from the source, from the router doing the computation, a shortest path tree. That is also saying that from that source, we could also send a copy of the packet along that tree to all the receiver in the network. So that is also a what? A very efficient flooding tree. Okay, that is a efficient multicast tree. So what multicast meant here is to send from one source to multiple receivers. Okay, so that the extra shortest path tree is also a multicast tree. So from that shortest path tree, we could do unicast, sending from one source to one destination. One can, of course, exploit that to send from one source to multiple destinations. And in the meantime, guaranteeing that it's also the shortest multicast tree. Okay, so multicast OSPF, MOSPF, is a very nice and easy extension of OSPF. Oh, by the way, one can also configure OSPF to run in hierarchy, okay, such as this one here I'm illustrating. So you see, there are two levels of hierarchy here. At the lower level, area 1, area 2, and area 3. Okay. Inside each area, we could be running an OSPF, and all these internal routers within an area runs the same OSPF. It requires the same metric, link cost. And then at the higher level, you see, in the backbone of this local area network, in the backbone of this AS, we could have also multiple routers configured. So these are called the backbone routers in general. Okay, some of these backbone routers might be at the border, okay, of the AS. They are also the boundary routers. Some of these backbone routers, okay, are also, okay, the manager of the areas. Okay, so this guy here and here and here are the area border routers. Okay, so the area border routers, boundary routers, as well as the other backbone routers together form the backbone, and they will together run also OSPF, but that is independent of the OSPF running inside each of these areas. So this slide is pretty much repeating what I was just saying. In the example, we do have two levels of hierarchy. Okay, so at the lower level, we have these local areas, and at the higher level, the backbone. Inside each local area, the link state advertisements will only travel within the area. Okay? The link advertisements for the backbone network will be traveling only within the backbone. And each node, okay, in each area is going to know the entire area's topology. And the node inside an area will only know the direction, okay, to the border area routers in case the destination is outside, okay, of the area. So these area border routers, okay, will summarize the distance to the destinations inside its own area and advertise to the other area border routers. Okay, so that's how the area border routers discover each other at the higher level. Okay, and those advertisements will be shared by also the backbone routers and the boundary router.
All right, so that's link state routing, which can be secure and multiple level on its own. All right, now we move on finally to the inter-AS routing, the one and only inter-AS routing, which is called, now you see from the outline, BGP. All right, so the first video is to give you an overview of BGP. As you recall, it's much like a distance vector, but more precise path vector. So in the very first part of this video, you will hear Polly talking about how it's path vector again. Okay, but in the second half, you will hear Polly saying that, hey, distance vector is an endless loop of 3 steps, right? Upon receiving a distance vector, doing the Bellman-4 equation finds the best routes, and in case the distance vector has been changed, meaning better information discovered, right? You propagate the new distance vector further. Okay, so it's an endless loop of 3 steps. But in BGP, as it runs, as it's a very important protocol that needs to interconnect with the intra-AS routing. BGP is endless loops of 4 steps. Getting the reachability information before it can start finding what's the best AS path. There's one more step. That reachability information needs to be propagated to all the intra-AS routers. Recall when Polly was talking about inter-AS, intra-AS routing interplay, it is important that all the intra-AS routers know about these paths, AS paths, to other domains on the internet. Okay, so get the reachability information, propagate the reachability information, which is essentially the path vector, okay, within all the intra-AS routers, and then work on what is the best path. And what's very different in BGP is that the way you get the best path, well, one can do it naively, taking the shortest AS path, okay? But guys, if you think a little bit more, right? An AS can be large or small, right? If you have a shorter path, but that path has a large domain in it, right? It might not really be shorter in terms of the delay, okay, going to the destination. So think about deciding what is the best path. In BGP, we often just say a good path instead of the shortest AS path. But you might hear Polly saying shortest AS path in the video, especially in the introduction, okay? But let me try to correct Polly myself. Let's take the best path, okay, the good path. Okay, so the third step, unlike the second step of distance vector, find the shortest path. We find the good path, and this good path could be more because of policy, okay, not because of shorter distance or longer distance, because you just don't know which AS goes a longer distance or a shorter distance, okay, in terms of delay. And the last step then is to propagate the reachability information further, okay. But in BGP, the propagation of the reachability information is also selective. There could be multiple options. In that case, you propagate probably selectively. But if there's only one, then of course, okay, you report the only one there is, right? So BGP, in the second half of the video, it's very much like the distance vector, but it's now an endless loop of 4 steps, a bit more complexity. And therefore, you see that this video is also a little bit long. Okay, 5 minutes.
Now the second big category, the inter-AS routing. There's in fact just one protocol defining the category, the BGP. Now this is also the routing protocol that runs on all these gateway routers, okay, that are higher in the internet routing hierarchy. OSPF, RIP, EDRIP, those are the intra-AS routing. So those runs on the regular routers, okay, within an AS. Now, network admin gets to choose one intra-AS routing protocol versus another, okay, as long as all the routers within the AS runs the same routing protocol. Similarly, at the higher level, these gateway routers, okay, in order to find a way to reach each other, they need to run the same routing protocol as well. You see, there's no need of having an alternative, okay, inter-AS routing protocol. Therefore, BGP here is the only inter-AS routing. Very critical. It plays the role of enabling all these packets being exchanged, okay, in the core of the internet. We'll talk more about BGP, but let me share just a little bit ahead of time. BGP here is based on the distance vector routing. To be exact, okay, it's based on the path vector routing. So in distance vector routing, the router tracks for each destination what is the shortest distance and what is the next hop, okay, along the shortest path to the destination. In path vector, okay, so this one running at the inter-AS level, the source AS will track for each destination AS what is the entire AS level path, inter-AS level path. So that inter-AS level path will contain all the intermediate ASs, okay,
along the way from the source AS to the destination AS. So what's nice about keeping track of the entire AS path is this. The source AS knows by default what is the next hop AS. And by counting the number of ASs along the way, you get a rough sense of the path cost as well. But the downside of tracking the entire path is that the memory requirement is higher. But this is okay, right, at the inter-AS level, because we try to aggregate destination IP addresses, right, into prefixes. Okay? And if we do that as much as we can, we are not actually storing a big vector containing one entry per IP addresses. Okay? Potentially, we just have a low number of these prefixes, okay, to span the entire IP address space. So path vector is exactly what BGP, this one and only inter-AS routing, is based on. First line, BGP stands for Border Gateway Protocol. And once again, it is the one and only inter-AS routing protocol that's holding the internet backbone together. To be more precise, it allows each AS the following. First, it allows the gateway router there for the AS to receive subnet reachability information from the neighboring ASs. This is very similar to distance vector. A router receives distance vector, okay, from the neighboring routers. So the gateway routers in the AS receive path vector from the neighboring AS's gateway routers. So by subnet reachability information, we meant the path for each destination subnet for each destination AS. Okay? And there are many of these destination ASs, therefore, we receive the path vector, okay, from the gateway routers of the neighboring ASs. Second step, the gateway router receiving such a path vector will then propagate it to all the internal routers, okay, including those routers are gateway routers to other neighboring ASs. Okay. As a result, okay, each of these routers within the AS can calculate what is the best path for a particular destination AS. The calculation can be based on what's provided in the path vector. For example, the path length, right? Or based on the policy of the organization owning the AS. Now, this is more and more likely the case how a router determines what is the best route. Okay? The policy can well be profit-driven, business-driven, security-driven, and things like that. And in the end, when a good AS path is selected for a destination AS, the border router there, okay, then can append, okay, the AS's AS number to the AS path derived, and then further propagate this to the neighboring ASs. Okay, so that completes the cycle of receiving path vector, doing the calculation, and then pass the path vector on to the rest of the internet. All right? And of course, okay, at the beginning, the AS gateway router will announce itself, right? So each AS is potentially a destination. It will announce itself's existence to the rest of the internet.
All right, so that was the very high-level overview. Next video, okay, Polly will talk a little bit more about this reachability information. You see that there's eBGP that is used to exchange the reachability information between domains. There's also iBGP. Those are to exchange the reachability information to the intra-AS routers. All right. So in the next video, you see Polly explaining more what this reachability information is about, which is essentially the path vectors. Okay. And in the second part of the video, you will see an illustration of propagation of the reachability information and how the ASs are appended, okay, to the AS path recorded in this reachability information, right? And you will also see an example, okay, showing that a particular network there, a particular destination there, how it's discovered by other domains on the internet. All right, so this video, 4 minutes.
One last point to make is just this: the reachability information, aka the path vector, when they travel across the border, go from one AS to another AS, this is actually part of the exterior BGP protocol. So in exterior BGP protocol, we established the exterior BGP connections to allow path vectors travel across borders from one AS to another. Now for path vector that is supposed to be sent internally to all the internal routers, then belongs to
the IBGP protocol, and they are sent through the interior BGP connections. And these are actually illustrated using this picture here. Okay, so if we focus on AS2, we do have two gateway routers, 2A and 2C. So you see these gateway routers connecting to other ASs. Yeah, there are exterior BGP connections to outside. Exterior BGP connections to outside. So eBGP, yeah, in red color. But in addition to that, 2N and 2C both need to send path vectors internally. Okay, so you see they went through the IBGP connections. All right, so IBGP connections in blue. So once again, these are gateway routers, and the gateway routers you see having both the red connections and the blue connections. Yeah, they run both the eBGP part of the protocol as well as the IBGP part of the big BGP protocol. Those BGP connections are often referred to as the BGP sessions. So these routers will exchange messages over semi-permanent connections. Yeah, the reason that they're called session is probably because it's semi-permanent, so it's on all the time, and occasionally you take it down and then restart it. Okay, so semi-permanent TCP connections. Now, TCP, BGP is a routing protocol, right? These messages we send should be at the layer 3, but TCP is actually a layer 4 protocol. Okay, how do you like this? On the other hand, TCP allows reliable data transfer. So would you prefer the path vector? So these messages that we're exchanging between the BGP routers, the path vector is being sent reliably or not? Yeah, to push it a bit further, what about using TLS, okay, the secure version of TCP? And if we use TLS, these BGP messages, these path vectors, will look more like an application level message. You think about it, you debate within yourself. Now, the messages we're exchanging between the BGP routers over the BGP sessions are these. Yeah, the path to all sorts of destination networks, the path to all sorts of destination ASs. In fact, yeah, altogether, we just call it the path vector. Okay. So BGP, again, a path vector protocol. And let me give you an example here. So let's say in AS3, okay, there is a prefix X. And this is the destination for packets coming from maybe AS1 or AS2. So AS3 that learns about this destination will need to announce, okay, advertise it to outside of AS3. So 3A here, okay, will need to announce, okay, its existence and pending its own AS number, so AS3 here. So this will be the AS path, okay, being advertised. This will be the AS path being sent in the BGP message to the other end of the exterior BGP connection, to the other end of the BGP session. So 2C here, okay, will receive the AS path, AS3, X. Okay. So AS3's gateway router 3A will advertise the path to AS2's gateway router 2C. So when AS3 does this, it's also saying that AS3 promises AS2 to relay packet, okay, on behalf of AS2 so that it can reach destination X. Right?
All right, so that was BGP, eBGP, and IBGP sessions and running on TCP. And an example of how the reachability information is accumulated over the ASs. And hey, this is all the time we have. And you know what, guys, check out the live chat box. Polly asked another quiz, a pop-up quiz, asking, would you like the eBGP or IBGP sessions run on UDP, TCP, or TLS? Okay, we know that BGP implemented on TCP, but what about you? What would you personally prefer? All right. So think about it. And with that said, that's all the time we have. So for the rest of the time today, try if you can answer the pop-up quiz number 2. So I ask you only say which one. Okay, so I did not ask you why because it's obviously why. All right. Yeah, yes, Sparrow. Yeah, give me what you prefer and say goodbye.
UDP, all right. Bye. TOS, TCP, TOS. Bye. All right. Okay, bye. All right, bye.